So there are some terms that we need to be aware of, and they are eigenvectors and eigenvalues. These are special cases. If M is a matrix and V is a vector, so when we multiply that matrix times that vector, if it can be found that that's equal to a scalar quantity, which we'll call lambda, and a scalar quantity is simply just a number, times V, if we can establish that, then this value here is the eigenvector, and this value of lambda is the eigenvalue. Now, given a value for lambda, there will be a particular vector. You may get multiple values for lambda. Each value of lambda you have to then go and calculate what is the eigenvector for this case. So M is a matrix, and we're talking about square matrix. V is the vector. So let's look at an example, and that'll help prove that, or help establish what we're talking about here. But before we go to that, if this is true, then we've got mv minus lambda v will be equal to 0. V is common to both, so we can take that out the back because it occurs at the back of each. So that'll be m minus lambda. Now we can't just put lambda because when you multiply that times that, we're not going to get something that which we can combine with a matrix, so it'll have to be lambda I. That'll be equal to 0. We know from what we've done with homogeneous equations that to get non-zero values for v, that the determinant of this must be equal to 0. So determinant of m minus lambda I equals 0 implies that we get non-zero vector, non-zero values for v, the eigenvector, and that's what we're looking for. We're looking for non-zero values of v. Zero values for this eigenvector are trivial, and we don't consider those. Okay, so let's just have a look at an example. So we're asked to find eigenvectors and eigenvalues for the matrix 0, 2, 2, negative 3. They may or may not exist, but we'll know when we try to solve them whether they do exist or not. So we use this here to solve for lambda first. But before we do that, we need to find m minus lambda I. So m minus lambda times the identity will be equal to 0, 2, 2, negative 3, minus lambda outside the identity. Now lambda outside the identity for a 2 by 2 is just 1's there. If I've got a lambda out the side, I multiply by the 1's, and these will be still zeros. So that will be equal to, when we work that out, we've got 0 minus lambda, so is negative lambda. 2 minus 0 is 2. 2 minus 0 is 2, and minus 3 minus lambda remains as is. So that's m minus lambda I. Now we've got to find the determinant of that and make it equal to 0. So the determinant of this will be equal to the determinant of minus lambda 2, 2 minus 3 minus lambda. Now to work out the determinant of that, we multiply along that diagonal, so it's minus lambda minus 3 minus lambda minus 4. 2 times 2, 4. equals, multiply out, and we get negative lambda times negative 3 is just equal to 3 lambda plus lambda squared minus 4, rearrange, lambda squared plus 3 lambda minus 4, and we say, okay, that's got to be equal to 0 because the determinant is equal to 0. If this is equal to 0, this is a quadratic, and the way to do these is to use the quadratic formula, or if it factorises, then I can see that that's going to be equal to lambda plus 4 times lambda minus 1 is equal to 0. So lambda has the values of 1 or negative 4. So there's two values. So we've got two eigenvalues. So these are my eigenvalues. 1 and negative 4. Two values for lambda that make this true. Okay, so next thing we've got to do is to we've got to find this vector here, because we know that m minus lambda I times this vector has got to be equal to 0. So now m minus lambda I is equal to this. So we can go, that's equal to minus lambda, and that'll be 2. And 2 minus 3 minus lambda. So we know that times v is equal to 0. So now we've got to find the different values of the vector. Firstly for lambda equals 1. What does this become? So it'll be equal to negative 1, 2, 2. Lambda equals 1, that'll become negative 4. Times my vector v, so go back up here, this times v has got to be equal to 0. Now we'll let v equal AB, and we can solve for A and B, and that's got to be equal to 0 or the 0, 0 vector. Okay, so how do we solve for A and B there? We can multiply out and we get negative A plus 2B equals 0, and 2A minus 4B equals 0. Using simultaneous equations we can solve, and we get A is equal to 2B. So therefore we can get the eigenvector. So if A is equal to 2B, we can say that the eigenvector is equal to, as long as the A value is twice as much as that, so it'll be just equal to 2, 1. So there is the eigenvector. So for lambda equals 1, the eigenvector is 2, 1. Similarly, if you put lambda equals, what was the other one? Negative 4. You can substitute in again, and you get the eigenvector as being equal to 1, negative 2 as the eigenvector. So eigenvalues and eigenvectors all revolve around the fact that a matrix times a vector is equal to some scalar times the vector. If that doesn't necessarily hold for all matrices, if we use that identity, we can actually find that the determinant of m minus lambda I is equal to 0. That will be true. If that is true, then we get non-zero values for the eigenvector, which is what we're after. So to find these, you actually first find m minus lambda I, find out what that is using the values for m, which we did there. You then find the determinant and know that that's got to be equal to 0, so you've got to actually, that allow you to find the values for lambda. They are your individual eigenvectors, eigenvalues. Now those values, for each of those, you've then got to go and find what the eigenvector will be, and you do that by working through that equation there, m minus lambda I v equals 0. I just used a and b for this is my v here, my vector, eigenvector. So when I substitute lambda equals 1, I get that, and it's got to be equal to 0. You get some simultaneous equations, so you can find a relationship between a and b here. And so 2, 1 would be an eigenvector, and then for lambda equals -4, you get -2, 1. Oh, sorry, 1, -2 for your eigenvector.